Welcome to part 3 on PPV monitoring for geophysical operations. This is the deep dive into sensor orientation. If one of your horizontal sensors is always aimed at the energy source, this is not a concern. But if the energy source could be somewhat off axis, then this is important. The main focus is vibrator operations, but the gist is still important for explosives. So the objectives of this presentation are to explore sensor orientation complexities when monitoring and to encourage critical thinking to refine best practices for accuracy and compliance. So from the ISEE guidelines on sensor orientation, the standard practice is to aim a horizontal sensor towards the energy source and document the orientation. Clause 4B is for when the horizontal sensor is not aimed towards the source energy. The ISEE recommendation is to aim a horizontal channel within 5 degrees of true north and document this information. No further explanation or discussion is provided. Well, if the sensor is not aimed at the energy source, the measured PPV on the individual horizontal components may be lower than actual, potentially leading to undetected non-compliance. So to simulate a sensor not aimed at the energy source, imagine recording individual 10 millimeter per second taps clockwise around the sensor. Now first, no matter where you tap on top of the sensor with a 10 millimeter per second tap, every reading should be 10 millimeters per second. And for geophysical operations, the standard for a recording geophone is plus or minus 10 degrees, which keeps the data within 98%. The ISEE was calling for a 5-degree accuracy, which is 99.6%. But this is just to look at the horizontal components. So with a perfect tap, the vibration is recorded as component vectors. The blue represents the PPV reading at the longitudinal sensor from 0 to 90 degrees. The red is a transverse sensor PPV recording from 0 to 90 degrees. If we were to look at the max of either sensor, it would look like this third display. That means at 45 degrees offset, each maximum recorded PPV is just 71% of the actual vibration energy. If your sensor is not aimed at the source, this is what you might be relying on during real-time monitoring. So, how do we recover the 10 millimeters per second? You have to use the Euclidean mean from both horizontal sensors, which is the square root of the sum of the squares of the horizontal measurements. This would yield the results shown in green. So here's a test I did by giving a sensor a tap at 45 degrees. You can see it yielded similar results on the longitudinal and transverse axes, 13.2 and 12.7 millimeters per second, which is expected. There is some vertical component, as this is not a lab setting. But we know the sensors were not aimed at the tap. In a lab setting, the same tap would likely have shown 18.19 millimeters per second had it just been on one axis. The breakdown is in the bottom left-hand corner. And this is a look at the waveforms showing where the peak particle velocity Euclidean norm is. Now, this is not a perfect solution and will likely yield slightly higher vibration values, but it is better than misunderstanding the data. The reason the results could be slightly higher is, even with the longitudinal axis pointed at the energy source, there would be vibrations measured on the transverse axis. The key takeaway is, horizontal PPV readings depend on your sensor orientation, and although not discussed, the vertical PPV is independent of the azimuth. So, compliance considerations. This is the same data displayed with different compliance thresholds. The Instant Health standard is red for transverse, green for vertical, and blue for longitudinal, and I've tried to stick with that convention for the most part. The basics here are each component, the transverse, vertical, longitudinal, must stay below the threshold. The PPV vector sum is not required for compliance, but these data are reliant on the sensor being aimed at the energy source. So why do horizontal vibrations matter? Well, horizontal vibrations are more likely to cause structural damage than similar vertical vibrations. And this is taken from a vibration monitoring expert, and Ken's statements confirm in the first paragraph, horizontal motions are key to damage prevention. Second paragraph, vertical motions affect different structures differently. And in the last paragraph, Ken confirms a best practice would be to use the Euclidean norm, or the square root of the sum of the squares of the horizontal components. Given horizontal motions are more likely to cause damage, and if your sensor is not oriented for accurate readings, you need to understand this and mitigate for it. And the reality is, often during testing, the sensors are usually aligned and aimed at the energy source at all offset distances. But in production, especially vibrosize, the sensors are often not aligned, which results in lower PPV measurements. The key takeaway, real-time production monitoring must account for sensor orientation, as does any post-processing evaluation. So in this slide, we're going to look at a small vibrator at a 2 meter inline offset and 2 meter cross-line offset to the sensor. The vibrator is positioned 45 degrees to the longitude and transverse sensors in this case. And the measured results are these. You can see it. The transverse in red just exceeds the USBM plaster limit, and the longitudinal in blue is barely within the USBM compliance. And we expect them to be quite similar at the 45 degrees. The vertical in green is well below the compliance, but again, that's independent. So now this is looking at the 3 individual maximums of our example. But we know the sensors are at 45 degree offset and may only be showing 71% of the actual value. So using the Euclidean mean or norm, this is a peak particle velocity vector sum of the horizontal components is 41.546 millimeters per second, which plots as a small black square. I did this by extracting the 15,000 recorded data points, calculated the Euclidean norm of the 2 horizontal components at every sample interval, and plotted the maximum. In real-time monitoring, the instrument only shows the max PPV of one component, doesn't tell you which one, the frequency, and the PPV vector sum. That means manual data extraction is required for full analysis. The bottom left-hand corner shows the extract of the data at the maximum Euclidean norm of the horizontal measurements. The data from left to right are the transverse, vertical, longitudinal components, the time, the Euclidean norm of the horizontal components, and lastly, the Euclidean norm of all 3 components. If our sensor or a second instrument was aimed at the energy source, we probably would have recorded this 41.46 millimeter per second vibration, which was non-compliant for the drywall threshold and significantly higher than what we originally recorded. When I first recognized this issue, I deferred to using the PPV vector sum of all 3 components, which is on the safer side. But it might be more accurate and more useful to be using the Euclidean norm of the horizontal components and the vertical component separately when working. So, what is the issue with the real-time monitoring? Time is money. With One vibrator in production, you could have a case like this. You get set up in front of the residence and you wait for the vibrator to approach and get it within range. In this case, we're along the far side of the road, so the cross-line offset may be 5 meters. Now, sweep 1. The vibrator sweeps for, say, 20 seconds and finishes. The instrument may collect data for another second. 9 seconds later, the vibrator is waiting at sweep position 2 as we assess the results. We do not have time to stop the instrument, realign it, level it, assure good coupling, do a sensor check, and begin monitoring. Now, for the most part, the transverse axis is still mainly pointed towards sweep 2. So we sweep again and we have 9 seconds to assess the results. The vibrator is now moved up to sweep 3 position, and the angle has increased significantly. Thus, we know the maximum recorded will be less than if one of the sensors was aimed at the energy source. By sweep position 4, we might just be recording 71% of the maximum. The challenge is the instrument shows us a maximum vibration level, the frequency, and the peak particle velocity vector sum, but it does not tell us which component was max. We can look at the real-time data in detail by selecting View Data Files, scrolling to the last record, and then we can see all of the results as we scroll a little more. But this takes a significant amount of time, and the vibrator is waiting to sweep. And we also do not know if a smaller PPV value at a lower frequency exceeded whatever threshold curve we are working with. Now, this slide ties to the Part 4 video about adequate testing and ensuring you analyze and understanding the data to help you with real-time monitoring. In the Part 4 video, I mentioned I have seen many projects defer to 12 millimeters per second as a maximum. That way you virtually don't have to worry about the frequency. If you defer to this method, you could safely just look at the max result, and if you were not pointed at the energy source, just use 9 millimeters per second as your max allowable, which is 71% of 12 millimeters per second. Now, this has negative implications for the subsurface data coverage, but it might be an easy out. So by this point, you should have plenty to think about. Or, on the other hand, you might just be nodding, wondering if there's anything I might say that you don't know. Okay, so slide 17. Consider these test data from a larger vibrator. On the left, we have the energy decay curves shown with both linear and logarithmic graphs. And on the right side, I've created a PPV decay curve 360 degrees around the vibrator. These are peak particle velocity vector sum data and assume a homogeneous response around the vibrator. In rough surface terrain or other situations like a ditch, there will be variations. Now, let's look at the individual components of a small vibrator as it approaches. This is from a smaller vibrator approaching the sensor. The sensor is at 2.8 meters cross-line from the vibrator as it approaches. The sensor orientation does not change. 3 of the graphs are all the individual sensor component responses, and the bottom right graph are all 3 components plotted together with the PPV vector sum. The vibrator is approaching from right, which is farther and becomes nearer on the left of the graph. If you look at the bottom right graph, the transverse vibration level in red has a higher reading than the longitudinal sensor results in blue at the far offsets. That's expected until the vibrator reaches about 45 degrees to the sensor. Once it becomes closer than the 45 degrees, the blue longitudinal vibration increases rapidly. And that's because it's coming right in front of the sensor. In this example, at the cross-line offset, the vertical sensor virtually controls the PPV vector sum. This slide is exactly the same sweeps, but a second sensor was positioned 9 meters back from the line. Again, as expected at the far offsets, the transverse recordings are higher than the longitudinal. At about the 12-meter offset, the longitudinal sensor starts increasing rapidly. From 15 meters to the nearer offsets, the longitudinal axis controls the PPV vector sum and not the vertical, and this is expected from surface sources. I've also seen data for the same sweeps with a sensor at a greater offset. I think it was back 18 meters, and it also yields the same predictable results. To look at a dynamite case, here's a quick look with the longitudinal axis aimed at the energy sources. This is a 0.5 kg dynamite charge in a 6-meter deep hole. The vertical component dominates the PPV vector sum / Euclidean mean, and as expected, the longitudinal axis aimed at the source is larger at all offsets than the transverse axis. The bottom right graph is a log plot of the 3 sensors and the PPV vector sum. It is clear the vertical component dominates, and the 2 horizontal axes increase as the source approaches. When the sensor is aligned like this, there is no need to use a Euclidean mean on the data set because you can see the 3 individual components. So the key takeaways: PPV readings depend on orientation and offset angle, and false compliance risk increases with, let's call it, sensor misalignment. So here are some thoughts. Conduct detailed testing and review and analyze the results. Recognize the transverse and longitudinal components are impacted by sensor orientation, and for dynamite blasts, the vertical component often dominates, except in shallow holes. So for real-time monitoring, sensor placement near the structure is best, but not always possible. Reorienting the sensor during production is often impractical, so you have to account for orientation error instead. If the sensor is some distance from the structure, you need to decide on whether you want compliance at the sensor or at the structure. If you accept non-compliance at the sensor, your risk assessment and data must fully support extrapolated values at the greater offset to the structure. And as you're working, predict the next sweep vibration levels and adjust your drive level before exceeding limits. And here are some things to consider, but they also have complexities. So what could work out nicely? A couple of things. Perhaps practical, perhaps not. Manually align the sensor each time. 2 co-located sensors at the location, the second instrument at 45 degrees to the first. Third, an instrument with a 4th sensor in it at 45 degrees to the other horizontal sensors could help mitigate this. A mounting bracket secured to the earth that would allow the sensor to be easily swiveled but still maintain good coupling. Set the sensor in front of the structure at a 45-degree offset and do not vibrate within the window in front of the structure. Maybe get manufacturers to update the display to include the Euclidean norm of the horizontal components to help you with the real-time monitoring. Or simply use a cutoff of 71% of the threshold. So, final takeaway, understand sensor alignment is critical for accurate PPV monitoring. Misalignment can result in false compliance readings, masking the risk. Testing and continuous data analysis will help you refine your best practices. It's that simple. Anyway, the next video is going to look at some vibrator considerations and probably address a couple questions like these two. And finally, Thanks for your time.